Picture a flash in the sky, not a meteor shower, but a single point of light, getting brighter every day. Astronomers confirm the unthinkable. A planet-killer asteroid, miles wide, is on a collision course with Earth. Impact is in 10 years. Your first thought might be Bruce Willis, a team of oil drillers, and a very big bomb. It makes for a great movie, but in reality, that would be one of the riskiest things we could do. The real plan to save the world is a lot smarter, a lot more subtle, and for the first time in history, it's already been tested. For billions of years, our planet has been a target in a cosmic shooting gallery with no way to fight back. The dinosaurs never saw the Chicxulub impactor coming, but we can. So, what happens when we spot the next one? Could we actually stop it? Stopping a Doomsday asteroid isn't as simple as pointing and shooting. The scale of the challenge is just mind-boggling. First, you have to find it. Space is vast, and many asteroids are literally darker than coal, tumbling silently through the void. Agencies like NASA's Planetary Defense Coordination Office, which sounds like it's straight out of a superhero movie, have the job of scanning the skies. They found most of the huge dinosaur-level threats, but thousands of smaller city-destroying asteroids are still out there, untracked. But let's say we find one. The next problem is speed. These things are hurtling through space at tens of thousands of miles per hour. Intercepting an asteroid isn't like hitting a target. It's like trying to hit a speeding bullet with another speeding bullet that you fired years in advance from millions of miles away. One tiny miscalculation, and you miss completely. This is where the Hollywood solution gets complicated. Why not just nuke it? Use our most powerful weapon to obliterate our greatest threat. The problem is, a lot of asteroids aren't solid rocks. They're rubble piles, loose clumps of gravel and boulders held together by their own weak gravity. Hitting one of those with a nuke wouldn't vaporize it. It would be like hitting a bag of sand with a cannonball. You'd just create a radioactive, expanding cloud of slightly smaller, but still civilization-ending, projectiles now heading for Earth like a shotgun blast. You've turned one big problem into hundreds of smaller ones. So, if brute force is that messy, what's the smarter play? The real strategy to save the world isn't about destruction. It's about deflection. It's a nudge, not a sledgehammer. Given enough warning time, you don't need to destroy the asteroid. You just need to change its speed by a tiny, tiny amount. A change of just a few centimeters per second, years before impact, is enough for the asteroid to miss Earth by thousands of miles. The key ingredients are time and technology. First, once we find a threatening object, we have to characterize it. We use powerful telescopes and radar to figure out its size, shape, spin, and most importantly, what it's made of. Is it a solid rock or a loose rubble pile? Knowing that is critical for picking the right tool for the job. And we are building an incredible toolkit. The main and most developed method is the kinetic impactor. It's basically a cosmic game of billiards. We build a robotic kamikaze spacecraft and slam it into the asteroid at high speed. The goal isn't to shatter it, but to transfer momentum, pushing it ever so slightly and changing its course. It's a clean, predictable, and direct way to give that crucial nudge. But what if the asteroid is too fragile, and we're worried a direct hit might break it apart? For that, we have a more elegant, almost poetic solution. The gravity tractor. A heavy spacecraft would fly alongside the asteroid for months, or even years, without ever touching it. Over time, the spacecraft's own tiny gravitational pull would gently and patiently tow the asteroid into a new, safer orbit. It's incredibly slow and needs a long warning time, but it offers amazing precision and control. Beyond these, scientists are working on even more futuristic ideas. Laser ablation would use powerful lasers to heat and vaporize the asteroid's surface, creating tiny jets of gas that act like thrusters to push it. The ion beam shepherd is a similar concept, using an engine to bombard the surface with a stream of particles, continuously pushing it over time. These aren't just sci-fi anymore. They're real concepts being designed in labs today. So we've laid out the playbook: cosmic billiards, gravity tugboats, and laser beams. It all sounds incredible on paper, a testament to human ingenuity. But does any of this actually work in the real world, millions of miles away in the vacuum of space? Before we get to the incredible proof, if you're finding this deep dive into saving the world fascinating, take a moment to subscribe. We break down the biggest questions in science and technology just like this every week. For decades, these ideas were just theories on a whiteboard. That all changed on September 26, 2022. This is a date that will go down in history. It was the day we stopped being passive victims and started fighting back. This was the day of NASA's DART mission, the Double Asteroid Redirection Test. The target was a small asteroid system about 11 million kilometers away. The main asteroid, Didymos, has a tiny moonlet orbiting it named Dimorphos. Dimorphos was the target. At 160 meters across, it was about the size of the Great Pyramid of Giza and posed zero threat to us. It was a live fire test in a perfectly safe environment. The DART spacecraft, about the size of a vending machine, traveled for 10 months for this one moment. In its final seconds, it streamed back breathtaking images. The lonely, rocky surface of Dimorphos grew from a pixel to a boulder field until the final, incomplete image was sent just before impact. Then, silence. Telescopes on Earth and in space, including Hubble and James Webb, all turned to watch. They saw a brilliant flash as the 570-kilogram probe slammed into the asteroid at over 22,000 kilometers per hour, creating a spectacular plume of debris that stretched for thousands of kilometers. The world held its breath. Scientists predicted the impact would change Dimorphos's 12-hour orbit around Didymos by at least 73 seconds. They would have called that a success. The results were better than anyone dared to hope. The impact didn't just alter the orbit by 73 seconds. It altered it by 33 minutes. The nudge was almost 30 times more effective than predicted. It turned out the blast of ejected rock and dust, a phenomenon called recoil, acted like a natural thruster, giving the asteroid a massive extra push. The DART mission was a roaring, unprecedented success. It proved unequivocally that humanity has the ability to change the path of an asteroid. So, we did it. Mission accomplished, right? We can all sleep soundly. Well, not exactly. DART was a monumental proof of concept, but Dimorphos was a tiny asteroid. A true planet killer would be dozens, or even hundreds, of times larger and more massive. Deflecting something like that would require a much bigger impactor, or maybe multiple impacts over time. The physics works, but the scale of the engineering required would be immense. And this brings us back to the most critical factor of all: time. Every single one of these deflection methods needs early detection. The kinetic impactor and gravity tractor are only effective with years, or ideally decades of lead time. If we discover a huge asteroid only a few months from impact, our options become terrifyingly limited. In that scenario, the controversial nuclear option comes back on the table. It's not the first choice, but it's a viable one. The plan wouldn't be to blow it up, but to detonate a nuclear device at a standoff distance, vaporizing one side of the asteroid to create a powerful push, all while praying it doesn't fragment. It's a high-stakes, high-risk maneuver, but it might be our only choice if we're caught by surprise. Finally, there's the human element. Deflecting an asteroid is a global problem. Who gives the order? What if altering an asteroid's path, even with a tiny chance of error, puts a different country at risk? This requires a level of international cooperation and trust that we are still working to build. The Planetary Defense Coordination Office isn't just about finding asteroids. It's about creating the global framework to decide what to do when we find one. So could we really divert a Doomsday asteroid? The answer is a qualified but resounding yes. The threat is real, an ever-present part of living in our cosmic neighborhood. But for the first time in our planet's 4.5 billion-year history, life here is no longer a helpless spectator. We are no longer the dinosaurs, gazing up in ignorance at our own doom. We have the knowledge, We have the technology. We have proven, in spectacular fashion, that it works on a small scale. The success of the DART mission marked the dawn of a new era, where humanity can actively defend its planet. The challenges ahead are to scale up that technology, to fund the search for every last threatening object, and to build the global consensus to act when the time comes. The question is no longer if we can protect ourselves, but if we'll be ready when we need to be. Human ingenuity has given us a fighting chance. What we do with it will determine our future.